Welcome to 7.8 Madison's Round Garden. It seems fitting with the spring and all the growth around us that we're talking also about a garden. Last year Madison won the city's Most Outstanding Garden Award for her square garden, and this year she plans to top that with her design for a beautiful round garden. Madison's design starts with a sprinkler in the center and concentric rings of colorful flowers surrounding the central sprinkler. Pavers will create both circular pathways and pathways that look like spokes on a wheel between the flowers. The sprinkler can be adjusted so it waters just the inner circle of the flowers, or it can be adjusted so it waters the entire round garden. Consequently, the flowers that need to be watered more frequently will be placed near the center of the garden, and those that need the least amount of water will be placed farthest from the center. The sectors of the garden will not all be the same size, since they need to accommodate different types of plants. Here's Madison's design for the garden. The number of degrees in each sector has been marked. Now, number 1 asks that we determine the angle measure for each of the arcs of the inner and middle rings of the garden, because she's only marked degree measures on the outer rings. So, based off of what we know that central angles here have the same degree measure as the sectors that they intercept. So if this central angle then is also 60 degrees and it intercepts this arc and this arc as well, that's going to be 60 and that's going to be 60 also. Okay? The same rule applies for this, 50 and 50, and so on all the way around the circle. So we'll have 40 degrees, 50 degrees, 60 degrees, 90 degrees, and 120 degrees also. So you can go ahead and fill those in so that we can move forward. That's the way you do number 1. Now, number 2 says that Madison needs to order pavers for the garden, and she plans to vary the size and colors of the pavers in different parts of the garden. So she needs to know the lengths of different portions of the path. We need to complete the table by calculating the missing arc lengths. Okay, so the arc length is the length on the circumference of one of those sectors, right? So we need to find the whole circumference of each of the circles, and then we can multiply that by what fraction of the circle we're working with. So for the whole circumference, we've got, let's see, distance from center is 10 feet, which means the diameter is going to be double that, right? And we know that the circumference, the total circumference, is pi times the diameter. So I'm going to multiply 20 times pi, and that will give me 62.8 feet of circumference. Okay? Now I will do 40 times pi, which is 125.6 feet. And finally, I will do 60 times pi, which is 188.4 feet. Okay, so those are the entire circumferences. Now what we can do is we can multiply those circumferences by the fraction of the circle that we're working with. So a 40-degree sector would be 40 360ths of the circle, right? So you could reduce that if you'd like to, or you can just take this fraction and multiply it by the total circumference. So it'll be 62.8 times 40 over 360. So the sector of the 10-foot circle, or the 10-foot radius circle, for 40 degrees, is 6.98 feet long. Okay, so 6.98 feet long. Now we can do the same thing with 20 feet, 125.6 times 40 divided by 360, and that gives us 13.96 feet. And finally, the same thing for the 30-foot radius circle, 188.4 times 40 divided by 360, and that gives us 20.93. So now you can go ahead and fill out the rest of this by using fractions of the circle times the circumference, okay? So go ahead, like this one will be 50 degrees over 360, and then it will continue on in that same fashion as you continue to the right. So go ahead and pause the video and fill all of those out. Now our next question after you fill all that out is that Madison began to notice some things that were interesting. Well, what do we notice? Actually, if we were to round each of these to 7, 14, and 21, check it out, and this is, 14, not 19. They're increasing by 7 each time. So what that means is that they are actually proportional. Okay, so our arc length and our radius are proportional to one another because they are all going up in a similar fashion. So now, one thing Madison noticed involved the ratio of the arc length and the radius of the circle. So now we need to complete this version of the table and state what we think that Madison noticed. So here we're going to take our arc length and divide it by the radius. Okay, so up here we've got our arc length of 7. And we're going to divide that by the radius of 10, okay? So it'll be 7 divided by 10, which is equal to 0.7. We'll do 14 divided by 20, which is equal to 0.7. Interesting. And then, let's see, 21 divided by 30, which is equal to 0.7. So now I want you to complete those for the rest of this table as well. Okay, now that you've gotten that all finished up, we're going to look at this last page here. As Madison examined these numbers, she realized that they behave in the same way that degree measurements behave. All arcs in the same sector have the same degree measure, and all arcs in the same sector have the same value for the ratio of arc length to radius. This made her wonder if these new numbers could be used as a way of measuring angles just as degrees are used. Later that evening, Madison shared her discovery with her older sister Caitlin, who's taking calculus at a local university. Caitlin told Madison that her new numbers for measuring angles in the terms of ratio of arc length to the radius are known as radians, and that they make up the rules of calculus math easier than if angles are measured in degrees. So here is our first taste of looking at things in terms of radians instead of degrees. We've talked a little bit about radians, but only in that we need to make sure that our calculator is not in radians so far. But now we're going to actually look at what radians are. So Madison learned so much from examining arc length of the sectors of her garden that she decided to examine the areas of the sectors as well. So we're going to complete this table by calculating the areas of the sectors of different rings of the garden. Okay, so now we're going to do this little section. Again, we're going to multiply our total, whatever the total is, by the fraction of the circle we're working with. So here's the fraction of the circle we're working with. And now we're looking at areas, right? So we need to find the area of a circle with a radius of 10 feet. So if we think about that, it's pi r squared. So we will have 314 feet squared because 10 squared is 100, and then times 3.14, we get 314. And then we're going to do the same thing with 20, excuse me. So we'll do 20 squared times 3.14, and that gives us 1,256 feet squared. 30 squared times 3.14 gives us 2,826 feet squared. And 40 squared times 3.14 gives us 5,024 feet squared. Okay? Now we're going to find the area of the sector, the degree sector, we're going to take the fraction of the circle that we're working with and multiply it by the total area. So we will take 314 times 40 divided by 360, and that is 34.9. Then we will take 1256 times 40 divided by 360, and that is 139.6 feet squared. Let me add or keep those units together. 2,826 times 40 divided by 360, that fraction of the circle we're working with, and that actually equals 314 feet squared. And 5,024 times 40 divided by 360 equals 558.2 feet squared. So now your task is to continue on finding the areas of individual sectors by taking the total area that we solved for in this column and multiplying it by the fraction of the circle that you're working with. Okay, so go ahead and complete that and fill that table out as well. Okay, now that you're finished with that, we're going to answer number 6. Do you notice anything interesting about this table? Well, in the last table, we saw that it went up in a linear fashion. We were adding 7 in the first 40-degree sector column. This one, though, it's not going up in a very linear fashion, right? We're going up by about 100 first, and then by like 190 something, and then by like 234 or so. So we're going up much more quickly. And if we were to actually create difference columns here and subtract and look at the first difference column and the second difference column, which I'm not going to do entirely right now, but we would actually find that the second difference column would be constant, which means that we are experiencing a quadratic function as we increase our radius just by 10 feet. And the interesting thing here too is, remember that the formula for the area of a circle is pi r squared. So it almost even makes sense that our functions would be increasing in a quadratic way rather than in a linear way with this one, compared to the circumference times pi, or 2 pi r, where nothing is squared, it's just a linear function also. All right, that's all we have for lesson 7.8. Enjoy your RSG.